Welcome back, students. Today we are going to solve some tutorial problems from chapter 7 of your ebook. That means chapter 8 of your paperback, textbook. Okay, so I have posted the tutorials as I wrote there. This chapter you don't have to actually solve all the problems, only topics which I have covered in last 2 video lectures, only those are important. And if you are able to solve those problems, tutorial problems, you are good to go. Okay, so the idea about this chapter is only to relate with the lab class you have. So I want you to know about it for sure, okay, but more thing you will learn about it during your lab class. Okay, so tutorial also accordingly what I have posted are easy questions. Basically they are in fact related to derivation or finding out the frequencies or velocity, wave velocity also. Those are easy basically. So that much only you need to know. So today we are going to solve some problems. So we'll start with 8.1. 8.1. So this is writing bracket, meaning that this is from the paperback. Okay. From ebook it is 7 2. Okay. So the question is that derive the equation for the natural frequency for a uniform chord of length L fixed at the two ends. The chord stretched to a tension T and its mass per unit length is rho. Okay. So this we have derived already, so only thing is right now we have to apply the boundary conditions. What it says is something like this one. This is the chord under tension, T is given and rho is given, length is also given, length is L fixed at both the ends like this one. From that you have to find out the natural frequency. So derivation that we did was general purpose, that could be applied different boundary condition. For example, one could be fixed, the other may be moving also. Yeah, so what we studied is a general one. Now we can apply the boundary condition and see how the solution looks like. So equation that we got was T del y or del square y over del x square equal to rho, then del square y over del t square. So this is the equation. Yeah. So solution, as we found out we solution equal to y equal to, we said will be some sort of a sine alpha t plus b cos alpha t. Okay, so that we got, and then we got the multiplied by, there were two parts. So this we call this just a minute, should be x here like this one, x, alpha x. So this alpha x like this one, this was part of px, and then we had second part, let's call this c sine omega t or omega n basically, plus b cos omega t. Right? So this we call q t. Right? Now it has to find out the this is a general expression. From there we have to find out how they relate, how omega, and we also related the omega. So from this solution we also got this condition. So what condition? So if you put here, what do we get? We get t, and from we have with respect to x, so we get alpha square from here, and from here we rho, and from here we will get omega square, so rho omega square. So this what resonance shift we got. So omega square equal to, we get alpha square T over rho. Okay, or this is basically omega is a natural frequency equal to given by alpha then T over rho. Okay. So this we got in our lectures. Only thing is now we have to understand how to find out alpha. Okay, so in order to find out alpha, we as I said earlier, we have to find out we have to fit the boundary conditions or initial condition. We are assuming in this case, since it is given, not assuming, it's given at the both location, it's equal to y is equal to 0 because fixed. So hence, if you put y is a function of x and t both, so at x and t, right, so is given by this one. Okay, so we write like y as a function of x and t is given like this one. So at y at x equal to 0 at all time is equal to 0. That really means if you put x value here, what do you get? We get this value is gone, right? So you put 0 here, yeah, so what do you get? We get b times 0 here, you get just b, and then you have c sine omega t plus b cos omega t equal to 0. Now this can vary, right? This is a function of t only, yeah, sorry, this is c, this will be a d, so this is d. Okay, d here. D. Okay, so b c sine omega t plus d cos omega t is equal to this. So this sine omega t cos omega t with time they are going to vary. So whole thing from here to here, the whole expression cannot be 0. So hence you have simply b equal to 0. So b is gone from here, hence you have y xt equal to a sine alpha x and like this one. Yeah. Now second thing is y l t is also equal to 0 because at x equal to l, x is going like this, right, and y is upward displacements. Yeah? So y l t is also equal to 0, and hence you put the value in this one. So b remaining we have what do we have? B equal to 0, so we have simply a here, a then sine then alpha, right, and then xl, right, this multiplied by the whole thing, right, so c sine omega t plus d cos omega t is equal to 0. Hence again from here to here cannot be 0, so this is 0, so we get sine alpha l equal to 0. That really means alpha l equal to, this will be 0 only when we have phi equal to n pi, right? Okay, and that's how the natural frequency comes into picture. So what do we have? We call alpha, let's call it alpha n equal to n pi over l, right? Okay, so this is how from here we get natural frequency, and how we have this one. So we have omega n is equal to alpha n root t over rho. Yeah, so this where is equal to, you write n pi over l and root t over rho. Yeah. So value of alpha we get from here, and then we put it here and we get the natural frequency, which will be look like this one. Yeah, so this is how you find out the natural frequency. Yeah. So that means here the basic fundamental frequency will be n equal to 1. So in that case it is going to have it like this. Yeah. The second will be n equal to 2. So in that case frequency will be just it is going to be the twice of that. Yeah? So in that case the mode shape will be like this. right? So it's going like this and like this, yeah. And so on. We'll have three nodes now, 4, 5, depending on n. So this is how the frequency will be omega 1, omega 2, omega 3, infinite, right? This omega infinite, because this is continuous system, so it will have infinite degree of freedom. So next is 7.1. So okay, so 7.1, and the paperback version is 8.3. Okay, so this question, which is actually related to this one only. What it is asking is find the wave velocity along a rope whose mass is 0.372 kg per meter when stretched to a tension of 444 Newton. Okay. So for solving this equation, we are going to use this equation only. However, here the details I am going to delete. Okay, so final equation we have like this. So the final equation we have y xt equal to, from here we have a sine, and we have alpha, instead of alpha we have n pi over L. This is what alpha is, times x, and then we have c sine omega t plus d cos omega t. So this is the equation we have right now, yeah. And the omega, we know here this omega is given by, for different n, here we have different omegas here, yeah. So for corresponding to n we have, so omega is given by n pi L t over rho also, yeah. So this is how they are related, yeah. Actually, you can write this equation in terms of c as well, and you can see here, if you see the del square y over del square x, so this one has a unit. If you see the unit of 1 over meter square, right? That, so 1 over meter, sorry, we have 1 over meter like this, yeah. Okay. Similarly, we have the different this del square y over del t square. We have unit of acceleration, right? So we have meter per second square. This is acceleration, right? So that's why we have unit of meter per second square. Hence, if we divide this by this one, so unit of del square y over del t square, okay, divided by del square y over del x square, will have unit of will be this meter per second square, and then divided by 1 per meter. So you get the units will be unit of meter square over second square, right? So this is the unit of velocity square, right? So this is the unit of velocity square. Okay. So actually that is the truth. Actually this is the velocity. So you can write in this case simply del square y over del t square equal to c square. This is the velocity, c square del square y over del x square, or simply equation you can write del square y over del x square equal to 1 over c square del square y over del t square, like this. You can write like that. Okay. So that really means if you compare with here, what do you get? So comparing with this one, what do you get? You get simply 1 over c square equal to rho over t, or simply you get c square or c equal to or c equal to root t over rho. This is the velocity, right? So this is the velocity of the wave, which will be equal to root t over rho. And you put the value of t is given and rho is given, you put this value, you get the velocity. You can also think in terms of equation also without doing the dimensional analysis. You can also from here you can find out. So one of the cases, for example, let's say at t equal to 0, we can have this equation. Let's say we start from this equation, right? So we have this equation, and from there we can have if y equal to 0, yx, initial condition, x at t equal to 0. So this is the initial condition, right? So initial condition, so you can assume, right? So this is equal to 0. So at t equal to 0, our reference t time maybe where it's a straight line, and then from there we can derive further. So that really means if you put the t equal to 0 value, so this will be gone and we will have d, which will be like this one. Since that really means the analysis we did earlier, so what we will get? Simply we get from that c, which becomes equal to 0, times d times we have basically like this, a sine n pi over lx times d equal to 0, and hence d will be equal to 0. So our equation becomes simply y xt is equal to a times c sine n pi lx times sine omega t. Right? Now this is the equation which can be written as in terms of two cos functions, right? So this whatever that is, we can write in terms of let's say a1, okay, cos half, right, n pi lx plus omega t, something like this we can write, okay, and then so this is sine, so cos minus, so it will be minus, and then we'll have cos half n pi l x minus omega t, something like that, right? Sorry, it looks like this one is wrong, so I think it should be another way. Okay, so it will be something like a, let's call it a1 here, and then this is sine, so cos a minus b becomes cos a b minus sine a b, right? So plus times becomes minus, so we will have minus term will come first, and there will not be any half there, so this will be cos n pi lx, then we'll have minus omega t, yeah, and then or maybe we can write this way, omega t first, so look, that way it looks good, omega t minus n pi l x, yeah, then minus cos, and then we'll have the omega t plus n pi lx. So we have some equation something like this one, right? Okay, so this makes is cos plus sine, this becomes cos minus sine, so we get like this one, and then divide 1/2 of that, so this will take care of that. So this is the equation we get. What we see here, this is a kind of the standing wave basically, right? The equation, the two waves which are being added together. So we can get from there also, what we see here will be if you see one wave here, this is one wave, the second wave is here. Both wave have same frequency omega omega, and this one from where we get C. So remember from the the wave equation will be typically like this one. Will be, let's call it B1. Then it will be sine, could be cosine also, sine, then will be 2 pi t over big T minus x minus lambda, right? So in this form, yeah, or simply if you expand that further, this will be given as equal to b1 sine, and then 2 pi, this becomes omega t minus, and if you look here, just a minute, we will write it up. So till here we have, so let's write it here. Okay, so y equal to b1, yeah, and then sine, then here we will have 2 pi, and we write like this, t over big T minus, so if you have t here over lambda, yeah, and then you have t over lambda, t right here again, we have x here like this, okay, so tx over lambda equal to b1 sine, then let's take this inside, so we get omega t here minus, you have 2 pi, this is time period, this is lambda, you know, so this is 1 over c, right, and then you have x over c, and this is t again, right, okay, so 2 pi over t here also you get, so equal to b1 sine omega t minus, so 2 pi over t is omega, so you get omega over c x here. So this is the equation, typically like this is the wave equation. So you can also compare this one. So here you have, if you sine, you can also write the wave equation could be also in cosine term. So what you compare, comparing that, what you get simply is n pi over L is equal to omega over c. Sorry. Right? That's what you can get, right? Or simply you get c equal to omega over n pi times L. Okay, so now this omega again is a function of n, right? So for different n will have different, so what you get from there is the, you know, omega n we got equal to n pi over L, that was alpha, and root t over rho, that's what we get, right? So we write it same thing here, so you get n pi over L root t over rho is omega n multiplied by L over n pi equal to root t over rho, simply. So that's what you get, c equal to root t over rho. So it's a long way of getting the same thing, but just you can do dimensional analysis also, you can do it. So anyway, so these things you have learned earlier, probably during your JE days. So, but just to repeat. One comment I have is, in the previous example we have yxt, that's came to be sometime, we can write it in terms of an, then we had sine n pi over L x, and then we can also write sine which has omega n right? Omega nt, like this one. Yeah. So basically, if you have a rope like this under tension, so the general solution, this is one of the fundamental, where n equal to could be 1, 2, 3 to infinity. In a real scenario, the solution, actual solution will be y, because all modes will be there. Just like in 2 degree of freedom system, we have 2 modes, right? And both actual solution, actual vibration could be a combination of 2 modes, right? So here, since there are infinite components or infinite waves basically, right, or infinite modes, so solution, general solution will be equal to n equal to 1 to infinity, and then we write an sine n pi over Lx, and we write sine omega nt. So this will be the general solution. You must have studied in your differential equation course as well. Okay, and this one, if that is the general solution like this one, you can here these are the coefficient. You can actually find out the coefficient basically, right? So all those things, then a Fourier series comes into picture and all. Yeah. So what you have, this one is actually kind of Fourier series. Yeah. So then Fourier series comes into picture, and accordingly there may be complicated wave. So instead of having a sinusoidal wave, the wave may look like something like this, because of the combination of various kind of frequencies, right, which is given by this one. Yeah. Now let's look at 7-5, which is 8.8, and find the velocity of longitudinal waves along a thin steel bar. The modulus of elasticity and mass per unit volume of steel are given. Okay, so values are given. So basically what it finds out, velocity of longitudinal wave. So c equal to what in case of longitudinal waves, right? So if longitudinal wave, in case of a longitudinal bar, what is the c? Again, from the equations, what equation you have? You have del square u over del, you had here e, right? Del square u over del x square is equal to, you had rho del square u over del t square. Yeah. In this case, note that this rho is actually mass, actual mass density. This is mass per volume. Okay. Compare this with the string under tension, where you had rho there also. So you had t del square y over del x square equal to rho del square u del square y over del t square. See the dimension. This is tension. This is a Newton. Here this is Newton per meter square. Yeah, this is just Newton here. So this rho, this can't be the same meaning here. So this is mass per volume, and this is mass per unit length. Yeah. So either you write this way, or you have to write also A. If this rho is, if you can also write like this one, EA del square u over del x square, and here this you can write rho del square u over del t square. But now this will be mass per length. Now you can write like this one. If you multiply A on both the sides, you can do. So be careful with that. Okay. So, but in any case, we have this meaning. Okay. So in the lecture, probably I taught you this way. So this also fine as long as you know what you are talking about. Yeah. So we will see, take this meaning. Okay. So because your in the problem also, the rho for this problem, the rho is given to be okay, whose mass is 0.372 kg per meter. So if this has per meter, then you have to take area consideration in that case. Sorry, actually in this case, in your case, the rho is given as in terms of kg per meter square, kg meter cube. Okay, so this is 8.8 or 7-5 of ebook. So this is rho is given like this one, so which has this meaning basically. So we will use this one only directly. Okay, okay, and modulus of elasticity is given Newton per meter square. So from this, meaning, okay, so here also we can actually same thing you can do, del square u over del x square equal to 1 over c square del square u del t square. Similar dimensional analysis you can do, and you can find out the c has to be here. Yeah, so that means c will be equal to e root e over rho. Okay, so e is given, this is Young's modulus, rho is given, so you can find out the velocity. So this is the wave velocity. So in fact 7-14, that is 8.816 also similar. Okay, similar. Here also you have to find out the velocity only. So all the velocity, although this is one is for the torsional system. Okay, but the similar, the expression will be similar. So instead of there you get del square, and then you will have a theta or phi, del square equal to 1 over c square, del square phi, del t square. So you get similar kind of expression there also, so you can get it. Now these two questions, 712, 8.13 and 715, okay, which is 8.14, both are similar, meaning only difference is, in first case this is for axial vibration case, and 715 is a torsional vibration. However, in both the cases there is a rod like this one, and this is fixed in the middle, okay, clamped in the middle. So clamped in the middle, so you have somewhere here it's clamped. Yeah. Okay, if that is the case, let us say we are solving the axial system. Yeah, so axial system, we have del square e del square u over del x square equal to rho, del square u over del t square, like this one, right? Our solution that we got will be similarly a, then we write a sine alpha t plus b cos alpha t, sorry, x in this case. Yeah, so x and x here, then we have we can write c, then sine, okay, and then omega t plus d cos omega t. So this is the general equation. Now we have to satisfy, only the difference is difference from earlier, the boundary condition is different. So we have boundary condition here, everything is fixed, for example. Yeah, so if you have x here starting from here, we can write like this one, or we have x from here plus minus we can do. So if your x is, we can write like this. Yeah, so let's have x starting from here, so like this, x like this. Okay, so this will be L over 2, this is minus L over 2, so that way you can write. So what it says, is clamped in middle, so u, this is the u as a function of xt, u as a function of xt is equal to like this one. So x 0 at all time will be equal to 0 because it's a clamped. Yeah, so you have a, then sine, if you put 0 here, so 0 automatically, then becomes b times c sine omega t plus d cos omega t equal to 0, hence v equal to 0. We get straight away like that. So that's why you should put x equal to 0 here, right? Equal to 0 here, so this is x. Yeah. So you get u xt is equal to simply a sine alpha x and then c sine omega t plus d cos omega t. So far we get this. Now second boundary condition we must find out alpha, and is there any force here? No force. So let's say point A and B, right? Or at x equal to plus minus L over 2, force equal to 0, and force equal to 0, that means sigma equal to 0, that means E A and del, this A is the area, remember this is not the same one, so let's distinguish, A1 we call it here like this one, A1 like this, so that's not A is area. Okay, so EA over del U over del X, so sigma, sigma is this, sorry, sigma is simply this is strain times E will be equal to 0. That really means strain equal to 0. Yeah? So simply del U over del X equal to 0, where at plus minus L over 2. If that is the thing, so then what do we get? We from here, so del U over del X equal to A1, and then you get alpha value, alpha, and then you get cos alpha x equal to 0. Yeah, so multiplied by all these things, c sine omega t plus d cos omega t all equal to 0, and hence since alpha is not equal to 0, we have cos alpha x equal to 0, where at x equal to plus minus L. Anyway, this is cosine function, so plus minus L over 2, sorry, so at x equal to plus minus L over 2 cosine function, so at the both of them it will be the same, actually you have only one constant that really means, so you have cos alpha and then x equal to, and x is cos x will be 0 when we have basically n plus half, right? So we have n, right, times pi, right? See where n equal to 0, 1, 2, 3 and so on. So we have n equal to 0, pi over 2, cos is 0, then we have n equal to 1, so we have 3 pi over 2, yeah, so there also it is equal to 0 and so on. So this is the equation you get. So that really means alpha times L over 2 is equal to this one. Okay, and hence we get alpha n equal to 2 over L multiplied by n plus half pi. So you get definite alpha, all others remains the same in this case. So boundary condition is the one which is going to get the value of alpha. Yeah, so you are getting this, then based on this you can solve other things automatically. Okay. So what you have to find out in both the year 13 and 14, natural frequency. Okay. For 813, which Jendra's frequency of this is given? Determine the proper length of alpha. Okay, so in case of 813, this inverse problem, you have to find out the length basically. So you have the length here. Yeah, so omega, relation with omega, as you know, omega, from this equation also you can find out. So E alpha square, alpha n square equal to rho omega n square. Yeah, so from you can find out from this one. So omega n equal to alpha n root E over rho, and this is 2 over L n plus 1 over 2 pi. So this alpha n multiplied by root E over rho. So this equation you can utilize. So this is the final equation. This equation will solve both the problem. In one case you have to find out omega n. So the other case you find out L given omega n. Okay? So of course this one is for the longitudinal problem. When you have a torsional problem, so instead of E you will have G basically. All other things remains the same. Okay. Now we will solve 7.18, which is 7-18 from ebook, which is 8.24. Determine the expression for the natural frequencies for a free bar in lateral vibration. Okay. So this is lateral vibration. So just lateral vibration, or this is a free beam. Free beam. Okay. Well, first we will understand the meaning. Okay, what do you mean by actually the lateral vibration? Okay. Actually, lateral vibration, you know, only the free. What is the meaning of free? Well, I am showing you the my daughter's xylophone actually, and what you see, these are the bar. So it's a musical basically. So you have bar length bigger, then this is being slowly decreasing, right? So from here to here you go, the length of the bar is getting smaller and smaller, right? So, and here you have a bigger the frequency, which is lower frequency, and when you go that side you have a larger frequency, so small. So this is a free beam. So because this is not fixed, what you see here actually, so this you can move basically, see here. Yeah, so it is not fixed, it's a free, and there is one very soft material here which is holding this one, you can see. So those are very something like a spongy material. So and also since it is a very loose basically, because of that this is a free beam. This pins are just to keep it in place. However, it is not really clamped here. Yeah, so that's why it is a free beam, and that's why the length plays an important role in this case. Yeah, so depending on the length, the frequency will be different. Of course, in any musical instrument, if you have the nice melody coming from some instrument, that only means it has not just one single wave. This is a combination of wave or harmonics. That means it has wave corresponding to all n's there, n equal to 0, 1, 2, 3. That's we have derived all the things are. So that's what it is telling, that in free beam, how you are going to find out the relationship or find out the wave equation. So we are going to write the equation first. The equation is del A square y over not a square, it will be to the power 4 like this, del x4 ei, right? This we got, and that is equal to we got rho, yeah, so this is rho, and then we have del square y over del t square. Okay, that's what we got. From this equation you can guess what should be what kind of rho it is. So this represents is basically the pressure. So this is a beam, and then remember from your solid mechanics, if you have a Qx, so Qx was given by this EI del 4y over del x4 was equal to Qx, right? So you remember. Okay, so this one actually is minus Q. So this one, if it is downwards, it should be minus Q. So this value, actually here equation you have minus value here. Okay, like this. So this is nothing but force per unit length. This is like this one, and what you see here is this is acceleration. So mass times acceleration is the force. Okay, so this should be force in terms of force only. This since the whole thing is force over length, this is force per unit length. Hence, what you get is this should be mass per unit length. Yeah, so this has to be mass per unit length. Okay, so remember it should be like that. Okay, if rho is the actual rho, meaning that the mass per unit volume, then in that case you have to multiply it by A. Okay, so to make it a mass per unit length. Okay, so here with this meaning, let's proceed. We already know the general equations, and that was y equal to, we called it from this side we had all the things like, let's call it something like this: A1 sine, we call it beta, right? So sine beta x plus A2 cos beta x plus A3 sine hyperbolic beta x plus A4 cos hyperbolic beta x, where, as you know, as we discussed earlier also, sine hyperbolic beta x equal to E beta x minus E to minus beta x over 2, right? It's like this. And the cos hyperbolic beta x equal to e to power beta x plus e to power minus beta x divided by 2. Yeah. So that means this exponential term which is being introduced here. So this is whole thing is px, and then qt term is also there. So a1 we call it, let's call it b1, and then this will be sine omega t plus b2 cos omega t. Right? So this is what y is, where y is a function of x and t both. Right? So like this one. Now this is a free beam. Only thing here is, if we everything we have to do the similar way. The only difference is that the boundary condition is different. So when you say free beam, what is the meaning of that? Free beam, if the beam is free like this one, okay, that means it is not clamped, nowhere any clamp is there. Yeah, so that really means that we have to see at the ends, as in the case of the rod which was clamped here, we looked at this, it was free end, this also free end, there was no force there. Similarly, in case of beam, there are two things, right? The one thing is V, right? So this V is not there, and second thing M, right? So 2 ends A and B, so VA and MA, VB and MB, both are 0. Okay, so free condition, free beam, meaning that bending moment at point A is 0, or what is the meaning of that? M is given by, in terms of M is given by EI del square U over del X square. This is M. So that really means EI, or simply del square U over del X square at X equal to, let's call this one as X equal to 0, right? And this is X equal to L. So X equal to 0 is equal to 0. That's what it tells, since bending moment is 0. And similarly, MB also 0, meaning that del square Y over del X square at X equal to L is equal to 0. So two boundary conditions we can apply here, right? So we take derivative of this one, double derivative of this one, and we make equal to 0, and from there we can find out which all things, the boundary condition we can find out, the value of beta we can find out, and we do the similar analysis as we did for other things, right? Okay, and similarly, the second thing is the shear forces, VB, VA and VB are also 0. So VA is equal to 0. That really means V equal to del M over del X, right? So this is the equation, right? So hence we get, you see here, that meaning is del Q Y del X Q equal to 0 at X equal to 0 equal to 0, and del Q Y del X Q at X equal to L is also equal to 0. Okay, so this is VA equal to 0, that will make VB equal to 0. And from there you can find out value of B. So let's apply this boundary condition and see what we get. Okay, so this is the Y. So we get del square Y over del X square will be equal to, we get A1 minus beta square A1 sine beta X plus A2 cos beta X. Okay, so that we get here, plus, okay, here we had A3, so here beta square. So cos hyperbolic or sine hyperbolic, if you take a double integral, then also it doesn't get minus like that, so that's why we get plus. So we have A3 sine hyperbolic beta X plus A4 cos hyperbolic beta X, like this. Okay, and at X equal to 0, everything equal to 0, that really, so just write this only. Yeah, so what is the value we get? Del square Y del X square X equal to 0, and we get these terms become 0 automatically. So we get minus beta square, and then T term is also there, the T terms, right? So meaning that this value, this will be also there. Okay, so minus beta square, then we have A2 coming from here, yeah, then plus beta square, and we put X equal to 0, then sine becomes sine H becomes equal to 0 only. Okay, so this is 0, and then we have A4, and the value here becomes equal to 1, right? So If x equal to 0, value equal to 1. So we have like this, equal to 0. Yeah, so what do we get? We get, since beta is not equal to 0, what we get from here is A2 equal to A4. That's what it tells you. Yeah. Okay. So next you can apply the we can apply this also, this one. Yeah. If you apply this one, then you will get like another condition, something like which will relate probably between A1 and A3, because these two terms will be signed in that case. Yeah, so you get relationship between A1 and A3. Okay. However, more important here is when relations you get for x equal to L. So at x equal to L, this expression is equal to 0, and this expression also equal to 0, right? So since both from here we get this one, for with the second one, this one V, for V or the shear force at A equal to also 0, you will get a relationship between A1 and A3, right? Because it will be cos here and cos here, so because of that you will get. Okay. So, but more important will be where what you get when equating the shear forces equal to 0 at x equal to 0 and x equal to L. Meaning that the shear forces are 0 here and here also. At x equal to L, shear force is 0 and the bending moment is also 0. So that means you will have you will get expression in terms of L now. Yeah. So what do you get in that case? Del square y will be equal to 0. So you get minus beta square. Then you get A1, which is equal to A4. So A1 sine beta L now you get, right? So similarly you get A2 cos beta L plus b square A3 sine h beta L plus A4 cos h beta L. Yeah, so then the time term will be there. So you get in now everything, time term is there, but this goes the other side, means everything that becomes equal to 0, right? And similarly the third derivative of this, okay, so meaning that is also equal to 0. So this one you are getting from this condition MB equal to 0. Similarly the VB is also equal to 0. From here what do you get? You get del cube y over del x cube equal to, from here we get further, so we get minus beta cube, then A1, this becomes cos beta x minus A2 sine beta x, here it becomes beta cube A3 sine h beta x plus A4, this becomes cos, this becomes sine here, sine h beta x, right? At x equal to L, this is also 0, right? So we have, instead of x, we have L here, we have L here, here L, you have, and here also L, like that. Everything that's equal to 0. So from these two equations, and also the coefficient you get from here for from this also, from this also, okay, at x equal to 0, what is the shear force? From there also we will get relationship between, this will tell A1 and A3 relation from here. So we have these two equations, this equation and this equation in terms of L there, and then we have coefficients here. All these four equations together will give beta as a function of n and L. Yeah. So beta is going to give for different n. This will have relate. Beta will relate to n and L, both length, and n is the n equal to 0, 1, 2, 3, 4 as appeared in other cases, the same kind of thing. And that beta, then we can relate it to omega n, right? The way we did earlier. And how the relationship will be, as we did earlier, we had EI, then beta 4 is equal to rho, and then we get omega square. Yeah? And hence this is beta, or beta n you can call it, right? Or omega n equal to this one, and from here you can find out omega n. So omega n becomes EI over rho root, and then you have beta n square, or you can write it beta n times L square divided by L square, like this. Yeah, because you get beta times L values from here. Yeah? So that you will put value here like this. Yeah. So this is lengthy basically. Yeah. So that's why I just told you the procedure, how to proceed. But this is the idea is to know basically how to solve it, because in your experiment next semester you will have like vibration of a beam, then you have to understand how it works basically, why both sine cosine as well as hyperbolic sine cosine come into picture. Yeah, so that is important. That's why I did this chapter, actually whole chapter, so that you understand. While doing the lab, you should not tell that this was not covered, we don't know anything about. So finally both should go hand in hands. Yeah, so you should understand the theory part in this course and the implication or application or the practical part in the lab.